before anything thought, something built. 4 billion years ago, Earth was a planet of fire. Molten rock, superheated vapor, a crust still learning to be solid. No forests, no oceans, no observers, just physics, playing with itself in the dark. And somewhere in that chaos, in the cooling edges of magma chambers, in the collision of pressure and time, something remarkable happened. Geometry appeared. Not designed, not programmed, not intended. The first crystals simply organized. Atoms found their places in lattices so precise you could call them beautiful, if beauty existed yet. Hexagons, cubes, octahedrons, perfect mathematical forms emerging from formless heat. And these weren't decorative. These structures, these geometries, were the planet's first architecture. The first time chaos learned to build with precision. Long before DNA, long before cells, long before anything we'd call alive, Earth was already writing rules in mineral form. But here's what we didn't understand until recently. These crystals weren't just rocks cooling down. They were records, time capsules. The oldest ones, tiny grains of zircon no wider than a human hair, survived 4 billion years of planetary violence. They witnessed the first rainfall. They formed when the first continents rose. They crystallized in Earth's earliest oceans, preserving chemical fingerprints of a world we'll never see. According to research published in 2024, these ancient crystals reveal that liquid water existed on Earth just 160 million years after the planet formed, far earlier than we thought possible. That means the stage for life was set almost immediately, not gradually, not slowly. The forces that built these crystals also built the conditions for everything that followed. And it's not just crystals. The same principle, order emerging from chaos through force and time, built everything else. Ocean currents that move more water than 100 Amazon rivers, wind patterns that seed forests across continents, thermal forces that crack mountains open and push magma to the surface, pressure waves that propagate through solid rock like thoughts through neurons. What we're about to uncover might change how we see patterns themselves, not as designs but as consequences, not as intentions but as inevitabilities. This is Omni, stories about life, matter, and the mystery in between. Like the video, drop your thoughts in the comments, and subscribe if you believe curiosity should never end. Picture the youngest rock on Earth, fresh lava just cooled, black and glassy, its surface still radiating heat you can feel from 10 feet away. Touch it tomorrow and you'll find something different. Microscopic crystals already forming, invisible geometries assembling themselves in the cooling stone following rules that predate continents. This is happening everywhere, constantly. Not just in volcanoes, in every phase transition, every moment where energy becomes structure. Water freezing into snowflakes, minerals precipitating in caves, salt crystallizing on coastlines. The universe keeps solving the same problem. How does formlessness become form? And the answer, across all scales, is the same. Through force. Not violent force necessarily. Just pressure, gradient, the push and pull of energy trying to equalize, heat meeting cold, pressure meeting release, saturated solution meeting air. In every case, when opposing forces meet, they don't just cancel out, they build, they organize. The planet has been doing this for 4.5 billion years, long before the first bacteria learned to split, long before amino acids assembled into proteins. Earth was already an architect constructing patterns that would outlast mountains, start with diamonds. According to recent research on mineral evolution, diamond was probably the first mineral ever to form, not on Earth, but in the expanding atmospheres of dying stars. Pure carbon, compressed by stellar fire at temperatures exceeding 400 degrees Celsius. Perfect octahedral crystals condensing in deep space, billions of years before our sun ignited. Earth inherited maybe a dozen of these minerals from the stellar nebula that became our solar system. A handful of geometric patterns frozen into dust. That's what we started with. Today, Earth hosts more than 4,400 known mineral species, from 12 to thousands. How? The answer is by getting complicated. Stage 1. The molten beginning. When Earth first formed, it was a ball of magma. Everything mixed together. Iron, silicon, oxygen, carbon, sulfur, all floating in superheated chaos. No structure, no order, just heat and motion. But as the planet cooled, something changed. The first solid crust formed, and when rock solidifies, atoms don't freeze randomly. They arrange themselves into the lowest energy configuration they can find. That means crystals. The cooling rock became a template, and atoms snapped into place like puzzle pieces finding their fit. Iron sank to the core. Lighter silicates rose to form the mantle. The surface became basalt, black volcanic rock, the planet's first skin, and in that basalt tiny crystals of olivine, pyroxene, plagioclase, the first library of geometric forms. Stage 2. Water arrived. Maybe from asteroids, maybe outgassed from the interior. Either way, suddenly Earth had oceans, and water changes everything. Water dissolves minerals, carries them, concentrates them. When seawater evaporates, it leaves behind salts, new crystals, different geometries, halite, gypsum, carbonate formations in shallow seas. According to geochemist Robert Hazen at the Carnegie Institution, water interacting with rock increased Earth's mineral diversity dramatically. Not by creating new elements, but by creating new contexts, new combinations of pressure, temperature, chemistry, where atoms could arrange themselves in novel ways. And here's what's remarkable. We know this happened by 4 billion years ago because we have the crystals to prove it. Zircon grains from Australia's Jack Hills, some as old as 4.4 billion years, contain oxygen isotopes that can only form in the presence of liquid water. These microscopic time capsules, each one about 100 microns wide, the width of a human hair, crystallized in granite. And granite only forms when wet rock partially melts and rises to the surface. So by 4.4 billion years ago, Earth already had continents. It already had a hydrological cycle. Rain was falling, rivers were flowing, and everywhere water-touched rock, new minerals were forming. Stage 3. Plate tectonics began. The crust started moving, recycling itself. Oceanic crust dove beneath continents in subduction zones. Rock was dragged down into the mantle, heated, partially melted and erupted back to the surface as chains of volcanic arcs. This process, subduction, melting, crystallization, is a mineral factory. It takes common elements and separates them, concentrates the rare ones, creates new chemical environments. Suddenly you get pegmatites, rocks crystallizing from the last dregs of granite magma, enriched in lithium, beryllium, tantalum, elements that don't fit comfortably in normal minerals. These incompatible elements cluster together and form exotic crystals: beryl, tourmaline, spodumene. Plate tectonics gave Earth about 1,500 new mineral species that smaller planets like Mars and Mercury never developed, because they cooled too quickly. Their interiors froze, no tectonic recycling, no mineral innovation. But Earth stayed hot, and heat means motion. Motion means pressure gradients, temperature differences, chemical potential waiting to be released. The planet became a self-organizing system, constantly creating contexts where atoms could discover new arrangements. And it's still happening. Right now, beneath the Southern Ocean, the Antarctic circumpolar current, the most powerful ocean current on Earth, is carving patterns into the seafloor. According to research published in Nature in 2024, this current carries more than 100 times the volume of all rivers on Earth combined. It extends from the surface to the abyssal depths, measures 2,000 kilometers wide, and has been flowing for at least 12 million years. As it flows, it sorts sediment. Heavy minerals settle first, lighter ones travel farther. The current writes its history in layers of seafloor deposits, each one preserving a record of flow speed, temperature, chemistry. Scientists drilling cores from these deposits discovered something unexpected. The current strength oscillates on a 2.4 million year cycle. Not randomly. The cycle matches a gravitational resonance between Earth and Mars. As the two planets orbit, Their gravitational interaction creates subtle changes in Earth's orbit. Nothing you'd notice, but enough to alter how much sunlight hits the surface. More sunlight means warmer oceans. Warmer oceans mean stronger currents, and stronger currents sort sediments differently. So Mars, 200 million kilometers away, is writing patterns into Earth's seafloor. Not through design, through physics, through the accumulated effects of gravity and time. The same principle applies to wind. The Hadley cells, circulation patterns in the atmosphere, redistribute heat from the equator to the poles. Hot air rises at the equator, flows poleward, cools, descends at 30 degrees latitude and flows back. This circulation creates trade winds, and trade winds push surface currents, and surface currents transport heat, and heat differences drive more wind. It's a feedback loop that's been running since Earth first had an atmosphere. No controller, no blueprint. Just the inevitable consequence of a rotating planet heated unevenly by a star, and it builds patterns. Deserts at 30 degrees latitude, where descending air dries the land. Rainforests at the equator, where rising air cools and releases moisture. Ocean gyres spinning in predictable directions, accumulating floating debris at their centres, all of it organised by forces that don't think, don't plan, don't intend. They just press and pull and sort. Now consider volcanoes. When magma rises and cools slowly, it can form columnar basalt, hexagonal pillars of rock, stacked like a honeycomb, each column perfectly geometric. The Giant's Causeway in Ireland, Devil's Postpile in California, these formations look designed, but they're not. They're cracks. As lava cools, it contracts. The surface cools faster than the interior, creating tension. The rock wants to minimise the surface area of the cracks. That's the lowest energy configuration. And the shape that tiles a plane while minimising edge length is a hexagon. So the cooling rock fractures into hexagonal columns, not because anyone drew them, but because geometry itself demands it. This is what we mean by first architecture. Not the oldest buildings humans made, the oldest structures Earth made, the geometry that existed before life. And it's everywhere once you start looking, in crystal lattices, in current patterns, in the branching of river deltas and the spiral of hurricanes, in the rhythmic spacing of sand dunes and the wavelength of ocean swells. Tonight, we're going to trace this thread, from the first crystals forming in stellar atmospheres, to the planet-wide circulation systems that move mountains of water, to the thermal forces that break continents apart and push magma to the surface. We'll explore how order emerges without designers, how patterns arise from nothing but pressure and time, how Earth became an architect before architects existed. Because understanding these forces changes everything. It reveals that intelligence isn't required for complexity, that beauty doesn't need intention, that the universe has been solving organizational problems for billions of years, and the solutions are written in stone, in current, in crystal. The geometry existed before life, but it created the conditions for life. And maybe, just maybe, life is simply the next phase, the moment when Earth's architecture became aware of itself. Let's begin where all organization begins, with atoms finding their place in the dark. Maybe the most honest thing we can say about the universe is this: it wants to be boring. Every system left alone moves toward equilibrium. Hot things cool, concentrated things disperse, differences smooth out, entropy increases. That's the direction time flows. That's what physicists call the second law of thermodynamics, and it's been true since the Big Bang. But here's the paradox. On the way to boring, the universe builds cathedrals. Think about what happens when molten rock cools. The magma is disordered, atoms tumbling over each other, vibrating with heat energy, free to move wherever thermal motion takes them. Entropy is high. The system is, in a thermodynamic sense, very close to maximum chaos. Then temperature drops, just a few degrees, and suddenly atoms start choosing. Silicon finds oxygen. 4 oxygen atoms arrange themselves around one silicon, forming a tetrahedron. That's the basic building block SiO4, the fundamental unit of almost every mineral on Earth. But these tetrahedra don't stay isolated. They link up, corners touching corners, chains forming, sheets, 3-dimensional frameworks. Each connection lowers the total energy of the system slightly, and as temperature continues to drop, there's a threshold, a crystallization point, where the energy benefit of staying organized outweighs the entropy cost. Below that temperature, atoms lock into place. The pattern becomes permanent. A crystal is born. This isn't random. According to Norman Bowen's experiments in the early 1900s at the Carnegie Institution, minerals crystallize from cooling magma in a very specific sequence. The sequence depends entirely on temperature and chemical composition, nothing else. High-temperature minerals form first: olivine, pyroxene, calcium-rich plagioclase. Then, as the melt cools further, different minerals appear: amphibole, biotite, potassium feldspar, quartz. Bowen's reaction series, as it's called, is essentially a recipe. If you know the starting composition and you control the cooling rate, you can predict exactly which minerals will form and in what order. The magma doesn't have options. It follows the path of least energy, crystallizing whatever structure minimizes the total system energy at each temperature. This is chemistry becoming geometry, elements becoming architecture. And the architectures are stunning. Quartz forms hexagonal prisms, halite makes perfect cubes, pyrite grows into octahedrons or dodecahedrons, calcite crystallizes as rhombohedrons, six-sided prisms with slanted faces. Every mineral has its own signature geometry, determined entirely by the size of its atoms and the strength of the bonds between them. You can't make cubic quartz, you can't make hexagonal halite. The geometry is dictated by atomic structure, which means it's dictated by quantum mechanics, by the way electrons arrange themselves around nuclei, by forces operating at scales 1 billion times smaller than the crystals they produce. This is what we mean when we say Earth was building before life existed. Not metaphorically, literally. Atoms were assembling into macroscopic structures with long-range order, with repeating patterns, with symmetries you can see with the naked eye. And they were doing it according to rules, mathematical rules, physical rules, that made certain outcomes inevitable and others impossible. Now scale this up. Not one crystal forming in one cooling magma chamber, but an entire planet crystallizing over hundreds of millions of years. When Earth first solidified, the minerals that formed were simple. Mostly olivine and pyroxene, magnesium and iron silicates. These are the minerals you find in the mantle today, miles beneath the surface, where temperatures are still high enough that only the most heat-tolerant structures can exist. But the surface cooled faster, and as it cooled, water vapor condensed. The first rains fell. Rivers formed. Erosion began. And suddenly, minerals weren't just forming from magma anymore. They were forming from solution. Imagine a river cutting through basalt. The water is slightly acidic. Carbon dioxide from the atmosphere dissolves into it, forming carbonic acid. That acid attacks the rock, breaking chemical bonds, releasing ions: sodium, calcium, magnesium, silicon. These ions flow downstream, dissolved in the river, invisible. Eventually the river reaches the ocean. The water evaporates, and when it does, the concentration of dissolved ions increases. At some point the solution becomes supersaturated. There's more dissolved material than the water can hold. And when that happens, the ions start precipitating out. They crystallize, just like cooling magma, but driven by evaporation instead of temperature change. According to research by Robert Hazen and colleagues, this process, water interacting with rock, increased Earth's mineral diversity by an order of magnitude. Because water creates new chemical environments, acidic water leaches different elements than neutral water. Salty water precipitates different minerals than fresh water. Hot water dissolves materials that cold water can't touch, and every time you create a new environment, you create an opportunity for a new mineral to form. By 4 billion years ago, Earth probably had about 420 different mineral species, still mostly silicates, still mostly simple combinations of silicon, oxygen, magnesium, iron, calcium, but diversifying. Clays forming from weathered feldspar, evaporites crystallizing in shallow seas, carbonates precipitating where marine chemistry allowed it. Each new mineral represented a different solution to the same problem. How do atoms arrange themselves to minimize energy in this particular set of conditions? And here's what's crucial. The planet wasn't trying to solve these problems. There was no goal, no target. no design, just physics, playing out its consequences across billions of tons of rock and water and time, but the results look suspiciously like problem solving anyway. Now add pressure, we've talked about temperature, we've talked about chemistry. But there's a third variable that controls mineral formation: pressure. And Earth, uniquely among rocky planets in our solar system, figured out how to use pressure as a tool. Plate tectonics changed everything. When did it start? Nobody knows for certain. Some zircon crystals show chemical signatures consistent with subduction, oceanic crust diving beneath continental crust, as early as 4.2 billion years ago. Others argue that modern-style plate tectonics didn't begin until 3 billion years ago or later. The debate continues. But whenever it started, once it started, Earth became capable of something no other planet could do. It could take surface materials and drag them deep into the mantle, subjecting them to pressures exceeding 100,000 atmospheres and temperatures above 1,000 degrees Celsius. At those conditions, minerals don't just melt, they transform. Consider what happens to basalt, the black volcanic rock that makes up oceanic crust, when it gets subducted. Near the surface, basalt is stable. Its minerals, plagioclase, pyroxene, olivine, are in equilibrium with surface conditions. But drag that basalt down to 50 kilometers depth, and suddenly, those minerals are unstable. The atoms rearrange. Plagioclase breaks down. The aluminum and silicon recombine into denser structures. Pyroxene transforms into garnet. New minerals appear, minerals that can only exist at high pressure. Jardiite, omphacite. These are metamorphic minerals born from transformation rather than initial crystallization. And if you drag that rock even deeper, 100 kilometers, 150 kilometers, the transformations continue. Olivine shifts from a relatively loose crystal structure to a denser one, then to an even denser one. Each transformation packs the atoms more tightly, allowing the rock to support the crushing weight of the overlying mantle. These phase transitions are predictable. They happen at specific pressure-temperature combinations, which means they happen at specific depths. Geologists can look at a metamorphic rock, identify which minerals it contains, and calculate exactly how deep it was buried before being exhumed back to the surface. The rock is a record, a diary written in crystal structure, and plate tectonics has been writing these records for billions of years. Every subduction zone is a mineral factory, taking common surface rocks and subjecting them to conditions that produce rare, exotic minerals. Some of these minerals get carried back to the surface in volcanic eruptions. Others remain trapped at depth until erosion or tectonic uplift exposes them millions of years later. But here's what's remarkable about this process. It doesn't just create new minerals, it creates feedback loops. When water-rich oceanic crust subducts, it carries water down with it. That water is locked in minerals, clays, serpentine, hydrated basalt. At depth, as the slab heats up, those minerals break down. They release water, and that water rises into the overlying mantle wedge. Water lowers the melting point of rock. Suddenly, mantle that was solid becomes partially molten. Magma forms. It's less dense than the surrounding rock, so it rises. Eventually it erupts at the surface, forming volcanic arcs, chains of volcanoes parallel to the subduction zone, like the Andes or the Cascades or Japan. These volcanoes don't just erupt basalt anymore. The magma has been modified. It's passed through the crust, melting some of it, mixing with it, incorporating its chemistry. The result is andesite, or dacite, or rhyolite, intermediate to silica-rich volcanic rocks that are unique to plate tectonic settings. And these rocks, when they cool, produce new minerals: hornblende, biotite, quartz, feldspars with different compositions than those in basalt, each one representing a different atomic arrangement, a different solution to the energy minimization problem at a different set of conditions. According to Hazen's mineral evolution framework, plate tectonics added roughly 500 new mineral species to Earth's inventory. Mars doesn't have them. Venus might, but we can't be sure. Its surface is too hot and too corrosive to study in detail. Only Earth, with its active tectonic recycling, sustained mineral innovation on this scale, and the process is still running. Right now, the Pacific plate is diving beneath Japan at about 8 centimeters per year. Basalt is being dragged down, transformed, melted. Water is being released. Magma is rising. In a few 100,000 years, that magma will erupt. It will cool. It will crystallize. New minerals will form, the factory never closes, but creation through heat and pressure is only half the story. There's another force shaping Earth's mineral diversity, and it works through destruction, erosion. Every crystal that forms, whether from cooling magma, precipitating solution, or metamorphic transformation, is stable only under specific conditions. Change those conditions and the crystal becomes unstable. It begins to break down. Feldspar, for instance, is one of the most common minerals on Earth's surface. It forms in igneous and metamorphic rocks at high temperatures, but expose it to rainwater at the surface and it starts to dissolve. The chemical bonds weaken, aluminum and silicon separate. Potassium leaches away. What's left is clay. Specifically, kaolinite, a mineral with a completely different structure than feldspar adapted to surface conditions. Thin sheets of aluminum, silicon and oxygen, stacked like pages in a book. Soft, easily transported by water, the mineral that makes mud. This process, weathering, is chemically driven mineral evolution. The planet is constantly recycling its surface materials, breaking down high-temperature minerals and replacing them with low-temperature ones adapted to water, oxygen and organic acids. And it's not just feldspar. Olivine weathers to serpentine and iron oxides. Pyroxene breaks down into clays and carbonates. Even quartz, one of the most stable minerals on Earth, eventually weathers, though it takes millions of years. Sand grains slowly dissolve at their edges, releasing silicon into groundwater. The weathered products get carried away by rivers, deposited in ocean basins, buried under layers of sediment. Pressure increases, temperature increases, and eventually, deep enough, those low-temperature minerals become unstable again. They transform back into high-temperature minerals. The cycle completes. Geologists call this the rock cycle. But it's really a mineral cycle, an endless transformation of crystal structures driven by the planet's internal heat and the weathering power of water. And here's the key insight. Every cycle adds information. When a river sorts sediment by grain size, depositing coarse sand in one location and fine clay in another, it's creating chemical gradients. Different minerals concentrate in different environments. Zircon, being dense and chemically resistant, accumulates in high-energy river channels. Clay minerals settle in quiet water. Evaporites form in isolated basins. These concentrations matter. They create ore deposits, places where specific elements reach high enough concentrations to be economically useful. Placer gold deposits in ancient riverbeds. Bauxite, aluminum ore in tropical weathering zones. Banded iron formations from ancient oceans, where photosynthetic bacteria produced oxygen that precipitated dissolved iron. Each deposit represents a place where geological forces, flowing water, chemical weathering, biological activity, sorted and concentrated elements. Not randomly, systematically. According to the physical and chemical properties of the minerals involved, the planet is an ore sorting machine, and it's been running for 4 billion years, slowly concentrating rare elements into economically useful deposits. We mine them, we call them resources. But really, they're geological solutions to chemical problems. They're the places where Earth's forces created conditions where specific minerals could dominate, and we only recognize them because we've learned to read the patterns. To see the signature of ancient rivers in the size sorting of grains. To recognize the chemistry of hydrothermal systems in the alteration patterns of volcanic rocks. To identify the pressure-temperature conditions recorded in metamorphic minerals. We're reading Earth's architecture, and the deeper we read, the more we realize. The planet has been engineering its surface for eons, not with intention, not with foresight, just with force and time and the inevitable consequences of thermodynamics. Now forget solid rock for a moment. Forget crystals and minerals and the slow grind of geological time. Focus instead on something that moves. Water. Not water sitting in lakes or trapped in ice sheets. Water in motion. Specifically, the Antarctic circumpolar current, the largest moving body of water on Earth, and possibly the most important circulation system the planet has ever produced. The numbers alone are staggering. This current transports roughly 135 million cubic meters of water per second. To put that in perspective, all the rivers on Earth combined move about 1 billion cubic meters per second. The Antarctic circumpolar current moves 135 times more water than every river. The Amazon, the Congo, the Mississippi, the Yangtze, all of them together, at any given moment. It extends from the ocean surface down to the abyssal seafloor, sometimes reaching depths of 4,000 meters. It measures up to 2,000 kilometers wide, and it flows continuously, ceaselessly, clockwise around Antarctica, connecting the Atlantic, Pacific and Indian Oceans in one unbroken loop. It's the only current on Earth that circles the entire planet. No land blocks it, no continents interrupt its flow. It exists because Antarctica exists, isolated at the South Pole, surrounded by open ocean, with no geographic barriers to deflect or slow the water moving around it. And it's been flowing, in something close to its current form, for at least 12 to 14 million years, possibly longer. Ever since tectonic forces separated Antarctica from South America and Australia, creating the Drake Passage and opening the Southern Ocean to circumglobal circulation. But here's what makes this current extraordinary. It's not just moving water, it's organising the entire ocean. According to research published in Nature in 2024, the Antarctic circumpolar current acts as a mixing engine for the world's seawater. Water from the Atlantic flows in, water from the Pacific flows in, deep water rises from below, surface water sinks. Everything gets stirred together in the turbulent chaos of the Southern Ocean, then redistributes to other ocean basins. This mixing matters because ocean water isn't uniform. Different parts of the ocean have different temperatures, different salinities, different dissolved oxygen levels, different nutrient concentrations. These differences drive the global ocean circulation, the so-called conveyor belt that regulates Earth's climate. The Antarctic circumpolar current is the blender. It's where the differences get homogenized, where extreme gradients get smoothed out, where the ocean resets its chemistry before sending water back north to the tropics. And the current doesn't just mix, it sorts. As water flows through the Southern Ocean, it encounters the Antarctic continent. The coldest water on Earth forms along the Antarctic coast, where sea ice freezes. When seawater freezes, it leaves salt behind. The remaining unfrozen water becomes extremely cold and extremely salty, which makes it extremely dense. This dense water sinks. It flows down the continental slope, cascades into the abyssal depths, and spreads across the ocean floor. This is Antarctic bottom water, the densest water in the ocean, and it fills the deepest parts of the Atlantic, Pacific and Indian basins. Meanwhile, at the surface, winds drive the Antarctic circumpolar current eastward. The Coriolis effect, Earth's rotation, deflects the flow, creating a convergence zone where surface water piles up. Some of that water sinks, becoming Antarctic intermediate water, which spreads northward at depths of 500 to 1,200 meters, so you have stratification, a three-dimensional sorting of water masses by density, with the densest at the bottom, the lightest at the top, and intermediate layers in between. Each layer flows at different speeds, in slightly different directions driven by different forces. It's a hydraulic engine. No moving parts, no fuel source, except the temperature difference between equator and pole, and the energy Earth receives from the sun. And it's been running continuously for millions of years. But the Antarctic circumpolar current isn't constant. It varies. Sometimes it flows faster, sometimes slower. And scientists drilling sediment cores from the Southern Ocean seafloor discovered something unexpected in those variations. The current follows a rhythm, not random fluctuations, but a repeating cycle with a very specific period, 2.4 million years. The discovery came from analysing grain sizes in deep-sea sediment. When the current flows fast, it carries fine sediment farther before depositing it. When it flows slower, sediment settles closer to the source. By measuring how grain size changes in core samples spanning millions of years, researchers at the Alfred Wegener Institute and Columbia University's Lamont Doherty Earth Observatory reconstructed the current's flow speed through time, and the pattern was unmistakable. Every 2.4 million years the current strengthened, then weakened, then strengthened again. The cycle repeated like clockwork, going back at least 5.3 million years, the full length of the sediment record they could analyse. This isn't a Milankovitch cycle. Those are orbital variations on timescales of tens to hundreds of thousands of years, the cycles that drive ice ages. This is something different, longer, and until recently, nobody knew what caused it. The answer, according to research published in Nature Communications in 2024, is Mars, not directly. Mars isn't reaching out and stirring Earth's oceans, but it is tugging on Earth's orbit. Both planets orbit the Sun, and as they do, their gravitational fields interact. Most of the time, these interactions cancel out, but occasionally, roughly every 2.4 million years, Earth and Mars fall into orbital resonance. During resonance, Earth's orbit becomes slightly more elliptical. The planet swings a bit closer to the Sun, then a bit farther away. The total amount of solar energy Earth receives, the insolation, increases by a small but measurable amount. More sunlight means warmer oceans. Warmer oceans are less dense. Less dense water creates weaker density gradients, which drives stronger circulation in the upper ocean, and that includes the Antarctic circumpolar current. So the 2.4 million year cycle in ocean current strength isn't caused by anything happening on Earth. It's caused by the gravitational dance of the inner solar system playing out over deep time. Lead author Dr. Adriana Dutkiewicz from the University of Sydney described the team's reaction. We were surprised to find these 2.4 million year cycles in our deep sea sedimentary data. There is only one way to explain them. They are linked to cycles in the interactions of Mars and Earth orbiting the Sun. This is humbling. It means Earth's ocean circulation, one of the fundamental systems regulating climate, is influenced by a planet 200 million kilometers away. It means the patterns we see in sediment cores, in ocean chemistry, in marine ecosystems are partly written by orbital mechanics operating on million-year timescales. The planet is listening to forces we can barely detect, and responding to them, not immediately, not in ways we'd notice in a human lifetime, but persistently, inevitably, over deep time. And all of this, the current strength, the water temperature, the sediment grain size, gets written into the geological record. Every year, sediment rains down onto the seafloor, dust from continents, carried by wind and deposited in the ocean. Microscopic shells of dead plankton sinking through the water column, fine clay particles suspended in the water for months before finally settling, volcanic ash from distant eruptions, fragments of rock eroded from underwater mountains. All of it accumulates, layer upon layer, millimetre by millimetre, building up at rates so slow you'd need geological timescales to notice, but the layers aren't uniform, they vary. Different grain sizes, different chemical compositions, different fossil assemblages. Each layer preserves a snapshot of ocean conditions at the moment it was deposited. When the Antarctic circumpolar current flows fast, it sweeps fine sediment far from the continent before depositing it. Coarser material dominates near shore. When the current slows, fine sediment settles closer. The grain size distribution shifts. Chemical composition varies too. During warm periods, when the ocean is well mixed and oxygenated, certain minerals precipitate more readily. During cold periods, when deep water becomes stagnant, different chemistry prevails, and fossils, microscopic shells of foraminifera, silica skeletons of diatoms, calcium carbonate plates of coccolithophores, reflect the surface temperature, the nutrient availability, the ocean circulation at the time they lived, so the seafloor is an archive, a library written in mud, and scientists have learned to read it. By drilling deep into the sediment, hundreds of meters below the seafloor, and bringing up continuous cores, they can sample millions of years of ocean history. By dating the layers using magnetic reversals, Earth's magnetic field flips polarity irregularly, and these flips are recorded in magnetic minerals in the sediment. And by analysing oxygen isotopes in fossil shells, which reflect water temperature and ice volume, they can assign precise ages to each layer. Then they can measure grain size, mineralogy, geochemistry, fossil abundance, and when they compile these measurements across millions of years, patterns emerge. Not random noise, patterns, repeating cycles, correlations between different variables, evidence of ocean circulation changes, climate shifts, ice sheet advances and retreats. The sediment remembers. Not in the way living things remember. There's no storage mechanism, no neural encoding. but in a more fundamental way, through physical and chemical properties that persist over time and can be measured, decoded, interpreted. When the 2019 International Ocean Discovery Program expedition sailed to the central South Pacific, to a point near the most remote spot on Earth, farthest from any landmass, and drilled cores 145 and 213 meters deep into the seafloor, they weren't just collecting rock, they were retrieving memory. Professor Helga Ards, a marine geologist at the Leibniz Institute for Baltic Sea Research and one of the study's main authors, explained the significance. The drill sites are in the vicinity of Point Nemo, the point on the Earth that is farthest from any landmass or island, where the ACC flows without any influences from continental landmasses. Using the sediment deposits in this region, we can reconstruct its mean flow speed in the past. In other words, by choosing a location where the current flows unimpeded, where no continents complicate the signal, they could isolate the pure effect of the Antarctic circumpolar current on sedimentation. And by analysing those sediments, they could reconstruct not just recent changes but millions of years of circulation history. What they found was remarkable. The current had varied dramatically through time. During glacial periods, when ice sheets expanded across the northern hemisphere and global temperatures dropped, the Antarctic circumpolar current slowed. During interglacial periods, warm intervals between ice ages, it accelerated. This makes sense. Colder global temperatures mean stronger temperature gradients between equator and pole, which drives atmospheric circulation, winds, more vigorously. Stronger winds mean stronger surface currents, and faster surface flow translates to more vigorous deep circulation. But overlaid on these glacial-interglacial cycles was the longer 2.4 million year rhythm. The Mars-driven orbital forcing, a slower, deeper oscillation that modulated everything else. Two cycles, operating on different timescales, interacting with each other, the planet responding to both. Now consider what all this circulation means for biology. The Antarctic circumpolar current doesn't just move water, it moves nutrients, it moves heat, it moves dissolved gases, oxygen, carbon dioxide. It moves plankton. It connects ecosystems separated by thousands of kilometers. When deep water upwells in the Southern Ocean, rising from the abyssal depths to the sunlit surface, it brings nutrients with it. Nitrogen, phosphorus, iron. These nutrients have been accumulating at depth, sinking as dead organic matter slowly decomposes. The deep ocean is nutrient-rich but sunlight-poor. The surface is sunlight-rich but nutrient-poor. Upwelling solves both problems. It brings nutrients to the light, and when it does, life explodes. Phytoplankton, microscopic algae, the base of the ocean food web, blooms in vast patches across the Southern Ocean. These blooms are visible from space, turning the grey water green with chlorophyll. They photosynthesize, converting carbon dioxide and water into sugar and oxygen, using sunlight as energy. Zooplankton, tiny animals, mostly crustaceans, feed on the phytoplankton. Krill, those small shrimp-like creatures that exist in almost unimaginable abundance in Antarctic waters, consume phytoplankton by the ton. And krill, in turn, feed everything else. Penguins, seals, whales, seabirds. The entire Southern Ocean ecosystem runs on krill, and krill runs on phytoplankton, and phytoplankton runs on upwelled nutrients brought to the surface by the Antarctic circumpolar current. The circulation creates the conditions for life. Not intentionally, not teleologically, just as a consequence of physics. Cold, dense water sinks. Warm, less dense water rises. Nutrients get transported, and wherever nutrients meet sunlight, photosynthesis happens. But there's another role the current plays, less visible, but perhaps more important for the planet as a whole. It regulates carbon. Phytoplankton, when they photosynthesize, absorb carbon dioxide from the atmosphere. Some of that carbon gets respired back immediately, but some gets locked into organic matter, the bodies of the phytoplankton themselves, or the zooplankton that eat them. When these organisms die, they sink, and when they sink, they carry carbon with them. Down through the water column, some gets consumed or decomposed on the way down. But a fraction, maybe 1%, maybe less, reaches the seafloor, and once there, buried under sediment, that carbon is removed from the active carbon cycle. It's sequestered, locked away for millions of years until tectonic processes eventually recycle it. This is the biological pump. And the Southern Ocean, with its vigorous upwelling and intense biological productivity, is one of the most important components of that pump. When the Antarctic circumpolar current flows fast, mixing is vigorous. More nutrients reach the surface, more photosynthesis happens, more carbon gets pulled out of the atmosphere. When the current slows, the reverse occurs: less upwelling, less productivity, less carbon sequestration. So changes in the current's strength, whether driven by Mars's gravitational influence, by glacial interglacial, climate cycles, or by human-caused warming, affect how much carbon dioxide remains in the atmosphere, which affects global temperature, which affects ice sheet stability, which affects sea level. The circulation isn't separate from climate, it is climate, or at least one of the fundamental engines driving it, and recent observations are concerning. According to Dr. Frank Lamy at the Alfred Wegener Institute, who led the 2024 study reconstructing the current's history, these findings provide geological evidence in support of further increasing ACC flow with continued global warming. In other words, as we warm the planet, the Antarctic circumpolar current is likely to speed up. That means more heat transported south toward Antarctica, which means faster ice sheet melting, which means accelerated sea level rise, and there's more. Faster circulation might also mean less efficient carbon sequestration, because rapid mixing brings carbon-rich deep water back to the surface, before biology can extract much of it. So the ocean's ability to absorb our carbon emissions could weaken. We're not just warming the air, we're changing the ocean circulation, and the ocean circulation has been running relatively stably for millions of years. Now we're perturbing it on timescales of decades. The planet will respond. It always does. But not in ways we control, and not necessarily in ways we'll find comfortable. Step back for a moment and consider what we're really talking about. The Antarctic circumpolar current isn't a thing, it's a process. Water molecules don't join the current and stay in it. They flow through it. They enter from the north, circulate around Antarctica, exit to other oceans. Individual water parcels might spend months or years in the Southern Ocean before moving on. Others pass through in weeks, but the current itself persists. The pattern persists. Even though the water continuously changes, even though every molecule is temporary, the structure remains. This is what physicists and mathematicians call a dissipative structure. It's a pattern that exists in a flow of energy or matter through a system. It's organized. It has coherence. It has identifiable boundaries and properties, but it only exists because of the continuous flow. Stop the flow, and the structure disappears. The current is geometry emerging from motion, order arising from turbulence, a pattern that wouldn't exist if the planet were static, if the ocean sat still, if heat distribution were uniform. But Earth isn't static. Energy constantly flows through it. Sunlight warms the equator more than the poles. That creates a temperature gradient. Temperature gradients drive circulation. Circulation transports heat. Heat transport moderates the gradient. It's a self-regulating system. Not because anything is trying to regulate it. Because the physics works that way. High gradients drive strong flow. Strong flow reduces gradients. Reduced gradients weaken flow. The system finds a balance, not equilibrium, because energy keeps flowing in, but a steady state, a dynamic stability. And within that stability, patterns emerge: gyres, eddies, currents, each one a temporary structure in an eternal flow, each one obeying fluid dynamics but manifesting in specific recognizable forms. The ocean doesn't have a blueprint, it has physics, and physics, given the right conditions, generates patterns as reliably as crystallization generates crystal shapes. This is what we mean by first architecture. The planet builds structures not from intent but from inevitability. Given Earth's size, its rotation rate, its distance from the Sun, its ocean geometry, the Antarctic circumpolar current has to exist. Some version of it is mandatory. The details might vary, but the broad pattern is predetermined by the boundary conditions. Same with crystal lattices, same with columnar basalt, same with sand dune spacing and river meander wavelengths and hurricane spiral shapes. The universe solves organizational problems, not with intelligence, with mathematics. The mathematics of energy minimization, pattern formation, self-organization, and sometimes those solutions look designed. They look purposeful. They look like someone sat down and engineered them. But nobody did. They just emerged. Now look up. The ocean isn't the only fluid moving across Earth's surface. There's another one, thinner, faster, more invisible, the atmosphere. Air doesn't seem like much. It's transparent. It has no colour, no taste, barely any weight we can feel. Walk through it and you notice nothing, except on the windiest days. But the atmosphere is every bit as dynamic as the ocean, more so actually. Air moves faster, responds quicker, carries energy more efficiently, and it follows the same principles. Temperature gradients, pressure differences, rotation effects, fluid dynamics. The mathematics that govern ocean currents also govern wind patterns. The physics that make water circulate in gyres also make air circulate in cells. Earth's atmosphere is organised into distinct circulation patterns, and the most important ones are the Hadley cells, massive vertical loops of rising and sinking air that span the tropics and subtropics. Here's how they work. At the equator, the sun delivers maximum energy. The ground heats up, the ocean's surface heats up, and that heat transfers to the air above. Warm air is less dense than cold air, so it rises. Powerful updrafts carry equatorial air upward, sometimes as high as 15 kilometers, into the upper troposphere. As the air rises, it cools, and as it cools, water vapor condenses, clouds form, rain falls. This is why the equator is wet. Torrential rain, daily storms, dense rainforests fed by abundant moisture. The atmospheric circulation delivers it. Not randomly, systematically. But the air doesn't just rise and stop. It has to go somewhere. At the top of the troposphere, it spreads outward, flowing north and south away from the equator. This is the upper branch of the Hadley cell, air moving poleward at high altitude. As it moves, it gradually cools further, and as it cools, it becomes denser. Eventually, around 30 degrees north and south latitude, the air becomes dense enough to sink. It descends back toward the surface, completing the loop. This descending air is dry, very dry. Whatever moisture it contained has already rained out over the equator. So when it reaches the surface at 30 degrees latitude, it's hot and dry, and it compresses as it descends, heating even further. This is where Earth's major deserts form: the Sahara, the Arabian Desert, the Kalahari, the Australian outback, the Atacama, all clustered around 30 degrees latitude north and south in the descending branch of the Hadley cells. Not coincidence, consequence. The atmospheric circulation creates zones of aridity, belts of dryness wrapped around the planet, positioned exactly where fluid dynamics dictates they should be. And the pattern doesn't stop there. The descending air at 30 degrees latitude reaches the surface and splits. Some flows back toward the equator, completing the Hadley cell loop. These are the trade winds, steady, reliable winds that blow from northeast to southwest in the northern hemisphere, and from southeast to northwest in the southern hemisphere. The Coriolis effect, the apparent deflection of moving objects caused by Earth's rotation, bends these winds. Air moving toward the equator gets deflected westward, creating the characteristic slant of the trades. Mariners have known this for centuries. Sail east to west in the tropics, and the wind is with you. Try to sail west to east, and you're fighting it. The rest of the descending air flows poleward along the surface. These winds eventually collide with cold polar air around 60 degrees latitude, creating the mid-latitude storm tracks, the zones of low-pressure systems, fronts, and changeable weather that dominate places like the Pacific Northwest, northern Europe, and southern Chile. This is the atmospheric engine. Solar heating at the equator drives the whole system. The uneven distribution of energy, hot tropics, cold poles, creates instability. And that instability resolves itself through circulation. Air rises where it's heated, sinks where it cools, flows along the surface and aloft, transporting heat from surplus regions to deficit regions, moderating the temperature extremes, making the tropics cooler than they'd otherwise be, and the high latitudes warmer. Without this circulation, the equator would be uninhabitable. Deserts would expand. Ice sheets would advance. The planet would be more extreme, less hospitable, more divided into zones of unbearable heat and unbearable cold. But the circulation runs. It's been running since Earth developed an atmosphere thick enough to support it, and it will keep running as long as the sun keeps shining and the planet keeps rotating. No maintenance required, no controller, just thermodynamics and rotation playing out their eternal dance. But the atmosphere doesn't operate in isolation. It's coupled to the ocean. They influence each other constantly, driving each other's motion, exchanging heat and moisture and momentum. Wind blowing across the ocean surface drags water along with it. The friction between moving air and the water below transfers energy. Surface water starts moving in the direction the wind blows. This is how the trade winds create the equatorial currents, water flowing westward across the Pacific, the Atlantic, the Indian Ocean. It's also how the westerly winds at mid-latitudes, between 30 and 60 degrees, create the eastward flowing currents like the Antarctic circumpolar current. But the coupling goes deeper. When wind piles water up against a coastline, that water has to go somewhere. Often it goes down, sinking beneath the surface and flowing back at depth. Or when wind blows parallel to a coast, the Coriolis effect pulls surface water away from the shore, and deeper water rises to replace it. Upwelling. Upwelling matters enormously for marine ecosystems. The deep water rising to the surface is cold and nutrient-rich. Wherever upwelling occurs, off the coast of Peru, off California, off Namibia, you find some of the most productive fisheries on Earth. Anchovies, sardines, hake, mackerel. These fish thrive in the nutrient-rich upwelled water, and entire economies depend on them. The wind controls this. Change the wind patterns, and you change the upwelling. Change the upwelling, and you change the ecosystem. And wind patterns do change. Not just seasonally, but on longer timescales. El Niño, the periodic warming of the eastern tropical Pacific, happens when the trade winds weaken. Normally, these winds push warm surface water westward, piling it up near Indonesia and allowing cold water to upwell off South America. But every few years, the winds relax. The warm water sloshes back eastward. Upwelling shuts down. The consequences cascade. Peruvian fisheries collapse. Rainfall patterns shift across the tropics. Droughts hit Australia and Indonesia. Floods hit South America. Hurricanes intensify in the Pacific and weaken in the Atlantic. The entire global climate system responds to a change in tropical Pacific winds. This is teleconnection, distant parts of the climate system influencing each other through atmospheric and oceanic circulation. A shift in wind here causes a current change there, which affects temperature somewhere else, which alters rainfall in yet another location. The planet is networked, connected, every region influencing every other region through flows of air and water and energy. And the flows follow patterns. Not rigid patterns, there's chaos, unpredictability, weather noise, but statistical patterns, preferred states, attractors in the system's behavior space. El Niño isn't random, it's quasi-periodic, recurring roughly every 3 to 7 years. The North Atlantic's oscillation, a seesaw in atmospheric pressure between Iceland and the Azores, has preferred phases it tends to inhabit. The Indian monsoon, which delivers most of South Asia's annual rainfall in a few months, arrives with remarkable regularity. These aren't coincidences, they're emergent patterns in a chaotic system, structures that persist despite, or perhaps because of, the underlying turbulence. And here's where it gets fascinating. The atmosphere operates on multiple scales simultaneously. There's the planetary scale circulation, the Hadley cells, the jet streams, the polar vortices. These are huge, persistent features driven by Earth's size and rotation rate, and the Sun's energy distribution. But within that large-scale flow, smaller structures form. Mid-latitude cyclones, low-pressure systems that bring rain and storms to temperate regions. These systems are typically a few thousand kilometers across, and last a few days to a week. They're born when warm and cold air masses collide, creating instability. The instability grows. A rotating low-pressure center develops. Fronts spiral outward from the center. Rain falls. Wind strengthens. Then, after a few days, the system dissipates. Each cyclone is temporary, but the storm track, the zone where these cyclones form and move, is persistent. The North Atlantic storm track, which funnels weather systems across the ocean toward Europe, has been active for millions of years. The position shifts slightly with climate changes, but the basic pattern endures. And within the cyclones, even smaller structures form. Thunderstorms, convective cells, updrafts and downdrafts. These might be tens of kilometers across and last only hours, but they're organized. They have structure, rising air in the center, sinking air at the edges, rain falling, lightning flashing, even smaller, tornadoes, waterspouts, dust devils, each one a vortex, a spinning column of air, highly organized but ephemeral. They form, they move, they dissipate, minutes to hours, sometimes just seconds. This is nested organization. Patterns within patterns within patterns. Each scale governed by its own physics, but all connected. The large-scale flow creates conditions for mid-scale structures. The mid-scale structures create conditions for small-scale features. And all of it emerges from the same fundamental equations, the Navier-Stokes equations of fluid motion combined with thermodynamics and rotation. Nobody designs a hurricane. Nobody plans its spiral bands or its eye wall or its maximum wind speed. But hurricanes follow rules. They form over warm water, at least 26.5 degrees in. They require low wind shear. They spin counterclockwise in the northern hemisphere, clockwise in the southern hemisphere because of the Coriolis effect. They intensify by extracting heat from the ocean and converting it to kinetic energy in their winds. Given the right conditions, hurricanes are inevitable. The atmosphere has to respond this way. It's the most efficient method available for transporting heat from ocean to atmosphere, from low latitudes to high latitudes. The hurricane is a solution to an energy transport problem, and it's a beautiful solution, geometrically elegant, thermodynamically efficient, dynamically stable, until it makes landfall or encounters hostile atmospheric conditions. The same goes for all the other atmospheric structures. Jet streams, ribbons of fast-moving air at high altitude, form where large temperature gradients exist. They're the atmosphere's way of transporting momentum and energy. They meander, creating Rossby waves, giant undulations in the jet stream path. These waves propagate, grow, decay, influence surface weather patterns. None of it is random, but none of it is deterministic either. You can't predict exactly where a hurricane will be 3 weeks from now. You can't forecast the jet stream position 6 months ahead. The system is chaotic, sensitive to initial conditions, prone to unpredictable shifts. But it's not arbitrary. It obeys physical laws. It explores a constrained space of possibilities, and within that space, certain patterns appear again and again, because they're stable, because they're efficient, because they're the natural consequence of rotating fluid on a heated sphere. Now connect the atmosphere to the surface. Wind doesn't just move air, it moves particles, dust, sand, salt spray, volcanic ash, anything light enough to be lifted or pushed. And when it moves these particles, it shapes the landscape. Start with sand dunes. In deserts, where loose sand covers the ground and vegetation is sparse, wind becomes a sculptor. It pushes sand grains along the surface, a process called saltation. Grains hop and skip, bouncing along, dislodging other grains, creating a cascade of motion. But the motion isn't random. Wind blowing over a flat sand surface creates ripples, small, evenly spaced ridges perpendicular to the wind direction. These ripples form because of feedback. A small bump in the sand surface disrupts the airflow. Turbulence increases on the downwind side of the bump, eroding sand there. That sand gets deposited farther downwind, creating another bump. The pattern propagates. Eventually, the ripples organize into larger structures, dunes. And dunes come in specific shapes, determined by wind direction, sand supply, and vegetation. Barchan dunes, crescent-shaped dunes with horns pointing downwind, form where sand is limited and wind direction is constant. Longitudinal dunes, long parallel ridges, form where wind direction varies seasonally. Star dunes, complex multi-armed structures, form where wind comes from many directions. Each shape is a solution to a different set of boundary conditions. The wind finds the shape that's stable under the local conditions. Once established, the shape persists, moving slowly downwind as sand erodes from the upwind face and deposits on the downwind face, but maintaining its form. The dune is a pattern in motion. Like the ocean current, like the hurricane, It's not a static object but a dynamic process. The sand is temporary. Individual grains enter and leave the dune constantly. But the dune shape persists, sometimes for centuries. Geologists can read dune shapes and infer past wind patterns. Ancient dune deposits, sandstones preserving cross-bedding structures from dunes that existed millions of years ago, tell us about atmospheric circulation in deep time. The geometry encodes the wind direction. The grain size indicates wind strength. The spatial distribution reveals climate zones. The wind writes history in sand, and the sand remembers once it's buried and lithified into rock. The same principle applies to loess, wind-blown silt deposits that blanket large regions of China, Central Asia, North America. During glacial periods, when ice sheets ground rock into fine powder, winds picked up that powder and carried it vast distances. Where the wind slowed, often at the margins of deserts or grasslands, the silt settled, accumulating in thick layers. These loess deposits are stratified. Each layer represents a different episode of dust deposition. Thicker layers indicate stronger or longer duration winds. Finer grain sizes suggest more distant sources or higher transport efficiency. Chinese scientists have used loess stratigraphy to reconstruct millions of years of monsoon history. When the monsoon was strong, vegetation expanded, stabilizing the surface, reducing dust emission. Thin loess layers formed. When the monsoon weakened, deserts expanded, winds strengthened, dust storms raged. Thick loess layers accumulated. The atmosphere's behavior, its circulation patterns, its wind intensity, its moisture content is recorded in sediment. Not just ocean sediment, but terrestrial sediment too. The planet documents its own history in multiple archives, using multiple recording media. And all of these archives tell the same story. Earth has been organizing itself for billions of years, sorting particles by size and density, stratifying materials by their physical properties, creating layers, gradients, patterns, not intentionally, not with foresight, but systematically, reliably, following physical laws that connect initial conditions to outcomes. But perhaps the most important thing the atmosphere does, more important than creating deserts or shaping dunes or driving ocean currents, is transporting water. Water evaporates from the ocean surface, about 1,000 cubic kilometers per day. That's an enormous amount. It doesn't just float in place. It rises into the atmosphere, carried by updrafts, spreading horizontally as wind moves it. This water vapor is invisible. You can't see it, but it's there, sometimes comprising several % of the air's mass, and it carries latent heat, the energy that was required to evaporate it in the first place. When the vapor condenses back into liquid water, forming clouds, then rain, that latent heat is released. It warms the surrounding air, and that warming drives more atmospheric circulation. Rising air creates low pressure, drawing more air inward, creating more uplift, more condensation, more heating. This is why tropical storms are so powerful. They're heat engines, extracting energy from warm ocean water by evaporating it, transporting it upward, condensing it, releasing the heat at altitude, using that heat to drive winds that evaporate more water. It's a positive feedback loop that can intensify explosively under the right conditions. But even without storms, water vapor transport is crucial. Moisture evaporated from the tropical oceans gets transported poleward by the atmospheric circulation. When it encounters colder air at mid-latitudes, it condenses and falls as rain, or snow at higher latitudes. This is how fresh water reaches the continents. Rivers don't create their own water, they collect water that fell as precipitation, and precipitation comes from evaporated ocean water, transported by wind, delivered inland by the atmospheric circulation. Without this transport, continents would be barren. No rivers, no lakes, no groundwater. Life as we know it wouldn't exist on land. The atmosphere is a delivery system. It picks up water at the ocean surface and drops it off over land. The total amount transported, about 40,000 cubic kilometers per year, is called the hydrological cycle. It's been running for billions of years, ever since Earth had both oceans and an atmosphere, and it creates patterns. Rainfall isn't uniform. Wet zones exist where atmospheric circulation favors uplift and condensation. the equatorial tropics, the mid-latitude storm tracts, mountainous regions where air is forced upward by topography. Dry zones exist where circulation favours descent and evaporation, the subtropics, the interiors of continents far from moisture sources. These patterns have been stable enough, long enough, that life has adapted to them. Tropical rainforests grow where rain is abundant and reliable. Grasslands grow where rainfall is moderate and seasonal. Deserts exist where rain is scarce. Change the atmospheric circulation, and you change the rainfall distribution. And that has happened repeatedly throughout Earth's history. During ice ages, the circulation shifted. Storm tracks moved. Some regions that are deserts today were lakes. Some regions that are wet today were arid. The climate isn't fixed. It's a dynamic equilibrium maintained by continuous flows of energy and matter. Perturb those flows, and the equilibrium shifts. New patterns emerge. Old patterns disappear. We're perturbing those flows right now. Adding carbon dioxide to the atmosphere, trapping more heat, warming the surface, strengthening the hydrological cycle. More evaporation, more water vapour, more intense rainfall in some regions, more severe droughts in others. The atmosphere will respond. It's already responding. The patterns are shifting. Not randomly. We can predict the general direction of change, even if we can't forecast the details. Warmer temperatures strengthen the monsoons in some regions, weaken them in others. Storm tracks shift poleward. Deserts expand or contract depending on local circulation changes. The planet is reorganizing, not willingly, not deliberately, but inevitably in response to altered boundary conditions. And the new patterns, whatever they turn out to be, will be just as logical, just as physically consistent as the old ones. They'll follow the same equations. They'll obey the same laws. They just won't be the patterns we evolved with. The patterns our civilizations were built around. The patterns our agriculture depends on. That's the risk. Not that Earth will stop organizing itself, it can't. Physics won't allow it, but that it will organize differently, in ways we're not adapted to, in ways we didn't anticipate. Step back far enough, and you start to see it. The crystal forming in cooling magma, the current circling Antarctica, the hurricane spinning in the Atlantic, the sand dune marching across the desert, they look different. They operate on different scales, involve different materials, persist for different durations, but they're solving the same problem. How does energy move from where it's concentrated to where it's not? How does the universe smooth out its gradients, dissipate its differences, slide toward equilibrium? And the answer, in every case, is through organization. This seems backward at first. We're taught that entropy increases, that disorder grows, that the universe is running down. And that's true for closed systems, isolated boxes with no energy flowing in or out. Put a hot object and a cold object in a sealed container, and eventually they'll reach the same temperature. The gradient disappears. Equilibrium is achieved. Maximum entropy. But Earth isn't a closed system. Energy pours in from the sun continuously. 361 watts per square metre at the top of the atmosphere, averaged over the planet's surface. That energy heats the ground, the oceans, the air. But it doesn't heat them uniformly. The equator receives more energy than the poles. The day side receives more than the night side. Gradients form constantly, and gradients drive flow. Heat flows from hot to cold. Pressure flows from high to low. Concentration flows from dense to diffuse. These flows are inevitable. Thermodynamics demands them. But here's the remarkable thing. The most efficient way for these flows to occur isn't through smooth laminar diffusion. It's through structure formation, through self-organization into patterns that accelerate the energy transfer. Consider a pot of water heating on a stove. At first, heat moves through the water by conduction, molecule to molecule slowly. But as the temperature difference between bottom and top increases, something changes. The water starts moving. Hot water rises. Cold water sinks. Convection cells form, hexagonal patterns visible from above, each cell a rolling cylinder of circulating water. These are Bénard cells, discovered by physicist Henri Bénard in 1900. They emerge spontaneously when a fluid is heated from below. No stirring required, no external forcing, just a temperature gradient and gravity, and suddenly the chaotic molecular motion organises into macroscopic coherent structures. Why? Because convection transfers heat faster than conduction. The organised flow is more efficient at dissipating the gradient than random molecular motion. So once convection starts, it reinforces itself. The cells persist, sometimes for hours, as long as heat keeps flowing through the system. This is a dissipative structure, a term coined by chemist Ilya Prigogine, who won the Nobel Prize in 1977 for his work on non-equilibrium thermodynamics. Dissipative structures exist in systems far from equilibrium, where energy or matter flows continuously through them. They're temporary. Remove the energy source and they vanish. But while the flow continues, they're stable. The ocean currents are dissipative structures. The atmospheric circulation cells are dissipative structures. Even crystals, in a sense, are dissipative structures. They form when heat flows out of cooling magma, and they represent the most efficient way for atoms to arrange themselves to minimize the system's free energy. The planet is full of them. Everywhere you look, flowing energy organizes itself into patterns, and these patterns share properties. They have boundaries, regions where the organized motion meets its surroundings. They have internal gradients. The flow isn't uniform within them. They exhibit scaling behavior. Similar patterns appear at different sizes. They're sensitive to boundary conditions. Change the external constraints and the pattern changes. Most importantly, they're self-maintaining. Once established, they actively preserve themselves. A river current carves its own channel, deepening it, reinforcing the flow. A dune shape, once formed, stabilizes itself. Wind flowing over it creates erosion and deposition patterns that maintain the geometry. A crystal growing in solution selectively incorporates atoms that fit its lattice, extending the pattern. The structures build themselves, not consciously, not intentionally, but through feedback loops connecting the pattern to the flow that generates it. And here's where it gets profound. These systems don't operate in isolation. They're coupled. They influence each other. The atmosphere drives ocean currents by pushing wind across the water surface. But the ocean influences the atmosphere by supplying moisture and heat. Warm water evaporates, creating clouds, releasing latent heat when the moisture condenses. That heat drives atmospheric circulation, which creates wind, which pushes the ocean. It's a loop. Each system forcing the other, each system responding to the other. The same coupling exists between the ocean and the seafloor. Currents deposit sediment. Sediment records current strength. But sediment also influences the currents. Seamounts and ridges create turbulence, channeling deep water, creating upwelling zones. Between the atmosphere and the land surface, wind erodes soil. Exposed soil changes the surface albedo, how much sunlight reflects back to space. Changed albedo alters local heating. Altered heating changes wind patterns. Between tectonics and climate, volcanic eruptions inject aerosols into the stratosphere, cooling the planet temporarily. But mountain building changes atmospheric circulation patterns, creates rain shadows, influences monsoon intensity. And weathering of exposed silicate rocks consumes carbon dioxide, regulating greenhouse warming over millions of years. Everything connects. Every subsystem couples to multiple other subsystems. The planet is a network of interacting processes, each one both cause and effect, each one shaped by and shaping the others. And out of this complexity, global patterns emerge. Ice ages and interglacials, cycling on 100,000-year timescales, driven by orbital variations but mediated by feedbacks between ice sheets, ocean circulation, atmospheric CO2, and weathering rates. The carbon cycle, moving carbon between rocks, oceans, atmosphere, and life, balancing on million-year timescales. The rock cycle, transforming igneous to sedimentary to metamorphic and back, operating over tens to hundreds of millions of years. Each cycle operates on its own timescale, but they're not independent, they interact. Fast processes modulate slow ones. Slow processes constrain fast ones. An ice age changes ocean chemistry, which affects carbonate mineral precipitation, which alters sediment composition, which influences the properties of metamorphic rocks, forming millions of years later. A volcanic eruption releases carbon dioxide, warming the climate slightly, increasing weathering rates, consuming CO2, eventually returning the climate to its previous state. But on a timescale of hundreds of thousands of years, the planet has memory. Not neural memory. There's no storage organ, no encoding mechanism, but physical memory. States now depend on states before. The current configuration influences what configurations are possible next. This is path dependence. History matters. Where you are determines where you can go. And yet, despite all this complexity, despite the chaos and the feedbacks and the nonlinearities, the system remains organized. Predictable patterns persist. The Hadley cells don't shift randomly. Ocean gyres maintain their structure. Plate boundaries stay where they are. There's stability within the complexity. Attractors in the system's state space. Configurations the system tends to return to, even if perturbed. Scientists call this complex adaptive stability. The system is far from equilibrium. It's turbulent, chaotic, sensitive to perturbations, but it's also structured, organized, resistant to complete randomization. It finds balance. Not equilibrium, that would be death, stasis, maximum entropy. But dynamic balance. Flow balanced by dissipation. Energy input balanced by energy output. Organization maintained by continuous reorganization. So here's the question that ties everything together. Why does order emerge from chaos? Not why in the sense of purpose. There is no purpose. But why in the sense of mechanism? What physical principle explains why energy gradients spontaneously generate organized structures? The answer isn't fully understood, but we have pieces of it. First principle, energy will flow. Thermodynamics guarantees it. Gradients will dissipate. Differences will smooth out. This is non-negotiable. Second principle, some pathways dissipate gradients faster than others. Convection moves heat faster than conduction. Organized flow transports energy more efficiently than random diffusion. Structure outcompetes chaos in gradient dissipation. Third principle, systems that dissipate gradients faster tend to persist and grow. They extract energy from the gradient. They use that energy to maintain and extend their organization. They're self-reinforcing. Put these principles together and you get a selection mechanism. Not natural selection. Nobody's reproducing here. But physical selection, structural selection, pattern selection. The patterns that are good at dissipating energy gradients grow. The patterns that aren't good at it fade. And over time, the system fills with efficient dissipators. This is the maximum entropy production principle, proposed by various physicists over the past few decades. The idea is that systems far from equilibrium don't just dissipate energy. They organize themselves to dissipate energy as fast as possible, consistent with their constraints. A river doesn't meander randomly. It meanders in a way that maximizes energy dissipation. The wavelength, amplitude, and sinuosity of the bends all follow mathematical relationships that optimize flow efficiency. A hurricane doesn't spin arbitrarily. Its structure, eye wall, rain bands, outflow channels, maximizes heat extraction from the ocean and conversion to kinetic energy in the wind. A crystal doesn't form in any arbitrary shape. It grows in the geometry that minimizes free energy, which is the geometry that most efficiently dissipates the latent heat of crystallization. The universe is solving optimization problems, not consciously, not with calculus, but through trial and error at the physical level. Patterns that work persist. Patterns that don't work disappear. And what works is defined by efficiency of energy dissipation. This is geometry as inevitability. Given the boundary conditions, Earth's size, its composition, its distance from the Sun, its rotation rate, certain patterns have to emerge. They're the solutions to the energy transport problem that the boundary conditions pose. You can't have a habitable Earth-like planet without ocean circulation. The temperature gradient between equator and pole demands it. You can't have a rotating heated atmosphere without Hadley cells. The physics requires them. You can't have cooling magma without crystallization. Thermodynamics doesn't offer alternatives. The specific details vary. The Antarctic circumpolar current is unique to Earth's current continental configuration. Different continental arrangements would produce different circulation patterns, But some version of ocean circulation is mandatory. The same logic applies across scales. You can't have a complex rocky planet without mineral diversity. You can't have liquid water oceans without weather. You can't have land masses without erosion. The patterns are inevitable. Not predetermined in detail, but predetermined in type, constrained by physics. The universe has a limited menu of solutions to energy gradient problems, and Earth's systems keep ordering from that menu. So what does it mean that geometry existed before life? Not as trivia, not as a curious fact about Earth's early history, but philosophically. What does it tell us about order, about complexity, about intelligence? For most of human history, we've thought of organisation as evidence of mind. Complexity implies design. Structure requires a designer. This was intuitive, obvious. Look at a watch, and you infer a watchmaker. Look at a cathedral, and you infer an architect. But look at a crystal, and you should infer what? A crystal maker? A divine geometer? Or just physics? The crystals don't care what we infer. They keep forming. Hexagons and cubes and octahedrons, emerging from cooling magma with mathematical precision, no mind required. No intention, no blueprint. Just atoms finding the lowest energy configuration, and geometry falling out as a consequence. This is what changes when you understand Earth's forces. You stop seeing organisation as evidence of intelligence. You start seeing intelligence as one possible expression of organisation. Life didn't invent problem solving. The planet was solving problems for billions of years before life appeared. How to dissipate heat gradients, how to sort materials by density, how to transport energy from where it's abundant to where it's needed. These aren't metaphorical problems. They're thermodynamic challenges with physical consequences, and Earth solved them, not with neurons, not with computation, with structure, with self-organization, with patterns that emerged because they were good at dissipating the gradients that created them. When life finally appeared, maybe 3.8 billion years ago, maybe earlier, it didn't introduce problem-solving to the planet. It inherited it. Life is built on the same principles that built crystals: energy gradients, thermodynamic optimization, self-organization through feedback loops. A cell membrane isn't fundamentally different from a crystal lattice. Both are ordered structures that minimize free energy. Both form spontaneously when conditions favor their assembly. Both persist because they're stable. DNA replication isn't fundamentally different from crystal growth. Both are pattern-extending processes. Both use template matching, DNA bases pair according to complementary geometry, just like crystal faces grow by incorporating atoms that fit the lattice. Even metabolism, the network of chemical reactions that powers life, is just sophisticated energy gradient exploitation. Cells extract energy from chemical differences between their inside and outside, using that energy to maintain their organization. It's the same principle as a hurricane extracting energy from the temperature difference between ocean and atmosphere. Life is continuous with geology, not separate from it, not imposed upon it, emerged from it, using the same physics, following the same rules. We're a pattern that learned to preserve itself through replication. That's special. It enabled evolution, complexity, eventually consciousness. But it's not a different kind of pattern. We're still dissipative structures, still temporary organizations in a flow of energy, still maintained by continuous input, doomed to dissolve when the input stops. The planet was building before we existed. It's still building. We're part of what it's built. 4 billion years ago, the first crystals formed, not the first objects, not the first structures, but the first geometries, the first time disorder organized itself into repeating patterns, the first time randomness gave way to symmetry. They formed in darkness. No light penetrated the clouds of dust and gas that surrounded the young Earth. No eye existed to witness them. No mind existed to appreciate their beauty. But they formed anyway. Diamonds condensing in stellar atmospheres, olivine crystallizing in cooling magma, zircon grains precipitating from granite melts, their structure encoding temperature, pressure, chemistry, information about a world that didn't yet exist in its final form. The geometry existed before life, but it created the conditions for life. The minerals that formed in Earth's crust and mantle and oceans didn't just sit there. They reacted. They weathered. They dissolved and reprecipitated. They created chemical gradients, concentration differences, energy sources, and somewhere in some pocket of water between rock grains, in some warm hydrothermal vent, in some tidal pool concentrated by evaporation, somewhere chemistry became complex enough to preserve itself, to copy itself, to evolve. Life emerged not from nothing but from geology, from the patterns that came before, from the planet's 4 billion years of problem-solving experience. We inherit that experience. It's written into us. The calcium in our bones comes from ancient seas, precipitated by marine organisms, recycled through the rock cycle, weathered into rivers, consumed as food. The iron in our blood comes from supernovae, incorporated into planets, concentrated by geological processes, extracted by life. We're made of Earth's architecture, and Earth's architecture is made of physics, working itself out over deep time, finding solutions, building structures, organizing chaos into pattern. This is the story we started to tell. How does chaos learn to build with precision? The answer is, it doesn't learn. It doesn't need to. The precision is inherent in the physics. The patterns are inevitable, given the boundary conditions. The planet doesn't have to try. It just has to be a rocky sphere, heated by a star, rotating, differentiating, cycling materials through its interior and across its surface. Everything else follows. Crystals form because atoms minimize energy. Currents flow because heat distributes. Winds blow because pressure equalizes. Structures emerge because they are efficient at dissipating the gradients that create them. The geometry existed before life because geometry is what happens when energy flows through matter. It's not special, it's universal. Every planet with enough energy input will self-organize. The details vary. Mars organized differently than Earth, Venus differently still, but the principle is constant. Order emerges from chaos. Not sometimes, not rarely, inevitably, consistently. Everywhere energy flows through systems capable of organizing. We look at crystals and see beauty. We look at current patterns and see elegance. We look at atmospheric circulation and see design. But none of it was designed. It was solved, physically solved, by a universe that doesn't plan but still builds, that doesn't intend but still creates, that doesn't think but still finds the patterns that work. And maybe that's the deepest lesson. Intelligence isn't required for complexity. Mind isn't required for order. Consciousness isn't required for organization. What's required is energy, time, and the freedom to explore possibility space. Give a system those three things and it will organize itself. Not randomly, not arbitrarily, but according to physical law, according to thermodynamic principle, according to the mathematics of pattern formation. The first architecture existed before life, but it taught life how to build. And now, 4 billion years later, we stand here. Patterns complex enough to understand patterns, structures organized enough to study organization, atoms arranged in configurations that can contemplate their own arrangement. We look back at the crystals forming in the dark. We read the sediment cores documenting current cycles. We measure the wind patterns shaping continents. We decode the messages Earth has been writing in mineral form, in erosion patterns, in stratified deposits. And we see the planet has been thinking all along, not with neurons, not with consciousness, but with structure, with form, with the geometry that solves problems because geometry is how the universe works. The forces that built everything you see, from the first diamond condensing in a dying star to the ocean current circling Antarctica to the crystal lattice in the rock beneath your feet, those forces are still operating, still organizing, still solving the same ancient problems. How does energy move? How does matter arrange itself? How does chaos become order? The answer was always the same. Through patience, through pressure, through time, through the slow, relentless logic of physics working itself out in stone, in water, in air. The geometry existed before life, but perhaps life is just geometry that finally learned to look at itself. And perhaps that's what we're doing right now, looking back at the architecture that built us, recognizing ourselves in it, seeing that the patterns we think with are continuous with the patterns that made us. We are Earth's forces, become conscious of themselves. We are the planet's architecture, asking how it got built. We are geometry, contemplating its own existence. And the answer, echoing across 4 billion years, is simple. We formed because forming is what matter does when energy flows through it. We organize because organization dissipates gradients. We exist because existence is thermodynamically favorable under these conditions. The first crystals knew this, not consciously, not deliberately, but through their existence, through their geometry, through the perfect mathematical precision of atoms finding their place in the dark. And now we know it too.